Hello, I am Dr. Pods, and today I want to show you how to sketch a simple Bode diagram for a low-pass filter. Let's assume that out of the analysis of your circuit or your system you get a transfer function g of j omega, which says 1 over 1 plus 0.01 j omega. 0.01 is the time constant of this filter, and it is in seconds. But what we're interested in is the critical frequency, which is the inverse. So omega c, the critical frequency, is the inverse of our time constant and is therefore 100, and the unit is radians per second. So the time constant is in seconds and the inverse is 1 over seconds, but we use radians per second here to denote that this is angular rate and not a frequency given in hertz. We also know that this is a low-pass filter. So this is a low-pass filter. And so the pass band of this filter is on the left-hand side, and the attenuation band is on the right-hand side. Finally, we know that at the critical frequency, this filter has a magnitude of -3 decibels. That is a typical property of first-order systems. And so with this, we can go into the Bode diagram and start our sketch. We put the critical frequency at the center of this Bode diagram. So we say 100 is the frequency that we put at the center of the diagram. Then the next stop is 1000 because we're in a logarithmic scale, and the one to the left is 10, and these are radians per second. Now we can put our critical frequency in here. -3 decibels is approximately here, so we know we have to go through this point. But first we draw our straight line approximations. And on the left-hand side, it's a pass band, so everything should pass through, and that means 0 decibel, no change to the magnitude. So we draw a straight line here, which goes like so. Straight line all the way to the critical frequency. Nope, didn't like that. Let's try again. Straight line all the way to the critical frequency. And in the attenuation band, we have again a straight line, but it has a slope of -20 decibels per decade. So what does that mean? We have to go 1 decade to the right, that is from 100 to 1000, and -20 decibels down. So we want to go through this point here. That defines our slope. And we draw another straight line at the slope of -20 decibels per decade. And this is what is called a straight line approximation. It's quite good, but you will find it doesn't actually go through this point of -3 decibel per decade. And the reason it is that the magnitude diagram isn't actually straight. It is actually smooth, so we can just use our imagination and by hand make a nice smooth transition here. The transitions from the one straight line to the other straight line and go through this point -3 decibels. And that is a decent sketch of the magnitude plot. The phase plot is related to this. So in the pass band, we have a phase that is typically around 0, so no change to the phase. So we can say we start at 0 on the left-hand side. In the attenuation band, because it is a first-order filter, we have a phase of approximately -90. And at the critical frequency, we are halfway between these 2 points at -45 degrees. And the way to connect this is using a sigmoid shape. It starts horizontal on the left-hand side, then goes through the center point and becomes horizontal again on the right-hand side. Takes a bit of practice to get this right, but you can draw this by hand, and it looks approximately like so. The second part of the transition can be a bit hard to draw, but this is a good approximation of our Bode diagram. We can see the pass band on the left-hand side, so we can mark this here as the pass band. We can mark this one here as the attenuation band, and we have our critical frequency, omega c, right at the center of the diagram. Of course, you might say, seems an awful lot of work. We could just ask a computer to do it. And you're right, we can. So I have prepared this, and you can put this transfer function into MATLAB. You use the function TF. You specify your polynomials as vectors. You can see here it states our transfer function. The one difference is that it uses S instead of j omega, which is just a question of notation. Then you use a Bode function to plot the Bode diagram, and you can see it looks exactly as we have sketched it. It goes exactly through this point here of -3 decibels, which is your critical frequency. You have your pass band on the left. You have your attenuation band on the right-hand side. You can see a nice smooth sigmoid transition with a phase, again hitting this point of -45 degrees at the critical frequency. And this is very nice, but what the computer doesn't do, it doesn't show you what this means. It doesn't explain to you that you have the passband on the left. It doesn't show you where the critical frequency is. And it doesn't show you that this one here has a slope of -20 decibel, 20 decibel per decade. So -20 decibel per decade as a slope here. Apart from that, of course, it is a very accurate Bode diagram. And so I hope you have seen here that you can either sketch it or you can ask the computer to do it. But if you ask the computer to do it, you need to understand where those critical points in the diagram are, because the computer just crunches the numbers. It doesn't actually show you what it means. I hope this was useful, and please have a look at my other videos for further problems.